Hi, everyone. So welcome to the ACE Medics KS3 Chemistry Energetics lesson. Hopefully all of you can hear me okay. So yeah, hi, my name's Henna, and I am a second year medical student at the University of Leeds. And I love chemistry in general, but I think my favorite chemistry topic will be hydrocarbons, which we'll actually just touch upon today. Yeah, this is our timetable for today. So for the first part, we're going to look at chemical reactions and look at some balancing equations. And then we're going to go on a little break, and then we will explore endothermic and exothermic reactions. And then we'll have a little break as well. And then we'll talk about catalyst and combustion, incomplete and complete combustion. And then we'll end with a clinical skills corner where we will be looking at the treatment for burns. So we have really exciting things coming up. Okay. So how this is going to work is we're going to have loads of questions to make sure you guys are picking up the content as we go along. We're going to have loads of exam practice as well. So we'll be looking at a lot of exam questions. We have another member of our team on the lesson today. So if you guys have any questions, you can just put it in the chat and our ACE will answer them. We'll have fun facts, and don't worry too much about writing things down, because we will have we are recording this session, so you guys will be sent the link to the video recording. So yeah, if any of you want to come back and review this stuff again, you can have a look at the video recording. So like I said, these are the learning points for today. We're going to look at chemical reactions, endothermic, exothermic reactions, catalyst, and combustion as well. Before we start actually looking at stuff, I just want to get an idea of how much you guys know about this topic already. So I'm going to put up a poll. And just maybe put in the poll how much do you guys know about energetics already. Do you know most of it? Do you know just a little bit? Are you an expert at it? Or is it just something that you haven't come across at all? So it really doesn't matter, because the whole point of this lesson is that we're going to learn about it. So how much do we know of this topic? So a lot of you are saying that that you know a little bit about it, so that's good. Hopefully by the end of this lesson you will know most of it or all of it. Okay, so first we're going to start off looking at chemical formulas. So what are chemical formulas? So a chemical formula is used to show an element or a so a chemical formula is used to show an element or a compound in a chemical equation. So an element is just one atom. So it's just the one atom. So for example, in the case of magnesium, we just have this is an example of an element. Okay, so magnesium is an example of an element. And compounds are when you have two or more elements joined up together in a chemical reaction, and that forms something called a compound. So that is two or more elements joined up in a chemical reaction. So we call that chemically combined. When two or more elements become chemically combined, that is called a compound. So in a chemical formula, we can show either an element or we can show these compounds. Okay, and the thing about chemical formulas is that it will tell you how many atoms it exactly has. So it shows you in exact atoms which make it up as well. So for example, sodium chloride has the chemical formula NaCl. Okay, so by looking at this, we can say that sodium chloride is actually a compound. How do we know it's a compound? Because we have sodium and chlorine joined up together. So they've undergone a chemical reaction to form this compound as sodium chloride. And like we said, chemical formulas shows you how many exact atoms are making it up and which ones are making it up. So, you know, in sodium chloride, when we have sodium and chlorine. Okay, so magnesium, we talked about, and we said that it's an example of an element because magnesium just has that one atom. Okay, and helium is also another example of a element because helium also just has one atom of helium. Okay, so So we're going to do another poll. From what we just said, can you guys tell me which is an example of an element? Okay, so I'm going to launch the poll. Which one of these is an example of an element? What do we think? Which one is the example of an element in this case? What are we thinking? Okay, so, and the poll. Yeah, so majority of you have said that sodium is the element, which is correct. Sodium is the element. How do we know sodium is the element? Because elements are just that one atom, isn't it? And sodium chloride, we already talked about, is a compound. How is sodium chloride a compound? Because it has more than one element in it. So it has the element of sodium and it has the element chlorine. And compounds, we said, are two or more than two. You can have more than two elements or atoms that have been chemically combined. And we call, when they undergone that chemical reaction, and we call that a compound. So similarly, sodium oxide is also an example of a compound. Why? Because sodium oxide has the element sodium and oxide. So what is oxide? So that is oxygen. Okay, so it has sodium plus oxygen, and sodium and oxygen have been they've undergone a chemical reaction and been chemically combined to form the compound sodium oxide. So carbon dioxide is also an example of a compound because carbon dioxide has the element carbon and oxygen. But can anybody tell me in the chat how many oxygen atoms are there in carbon dioxide? How many oxygen atoms are there in carbon dioxide? Who maybe put your answers in the chat? Yeah, so there are two oxygen atoms in, yeah, excellent. Yeah, so there are two oxygen atoms in carbon dioxide, and we know that because it has this di in front of it. Okay, so carbon dioxide is also a compound because it has two or more. So in this case, we can see that there is two or more because there's carbon and two atoms of oxygen. So they have two or more elements / atoms combined together to form this compound. So the example of element in here, so if we do a process of elimination, so we've said that sodium chloride is a compound, sodium oxide is also a compound, and carbon dioxide is also a compound. We know that sodium must be the element. So, good. Right, so let's have a closer look at chemical formulas, okay? So we already said that chemical formulas show you which atoms are making up that compound. So if you look here, H2O, who can tell me what that is? What is H2O? Again, maybe write your answers in the chat. What is H2O? Okay, so H2O is water. Yeah, so H2O is water. And from this chemical formula, yeah, so from this chemical formula, you can see that H2O is made up of hydrogen, and it's also made up of oxygen. But what this chemical formula is also telling you is how many atoms of hydrogen there are and how many atoms of oxygen there are. And what is telling you that is this small letter here that we call the subscript, okay? So this subscript, okay, is telling you that there are 2 hydrogen atoms and that there is 1 oxygen atoms. So how do we know that there are 2 hydrogen atoms? Because they've written the 2 right next to the hydrogen, and there's nothing next to the oxygen, so you know it's just 1 oxygen and 2 hydrogen atoms. Okay, similarly, so we talked about our carbon dioxide. The chemical formula is telling you exactly what atoms make up carbon dioxide, so you know that it's carbon and oxygen. And you guys have already said that there are 2 atoms of oxygen. So how can we work that out? Because this little number 2 that we call the subscript is written right next to the oxygen, showing us that there is 1 carbon atom and 2 oxygen atoms. Okay, so does that make sense for everyone? Yeah. Okay, so this is kind of a harder question, but who can tell me the formula for ammonia? I'm going to do the poll again. And I want you to tell me which one of these is the formula for ammonia. This is kind of a harder question, so I'll be really impressed if you guys can get this. Give you guys a few seconds. Let's see. Right. Okay, so majority of you answered. And the poll. Yeah, so the majority of you have said the right answer, which is A. Okay, so ammonia has the chemical formula NH3. Okay, so who can tell me how many hydrogen atoms there are in ammonia and how many nitrogen atoms there are in ammonia? So I should say that ammonia is made up of basically nitrogen and hydrogen. So how many nitrogen atoms are there in ammonia? Who can tell me how many? So yes, yeah, 1 nitrogen atom. And how many hydrogen atoms are there in ammonia? 3 hydrogen atoms. Yeah, so there are 3 hydrogen atoms in ammonia and 1 nitrogen atom in ammonia. So how can we tell that there are 3 hydrogen atoms? Because remember, the small letter here that we call the subscript is written right next to the hydrogen. So we know that there is 3 hydrogen atoms and 1 nitrogen atoms, okay? Right, let's go on the next slide. Okay, so these are just few more examples of the chemical formulas and compounds that you might come across. So it's good to keep them in mind. Okay, so we already talked about ammonia and it having the chemical formula NH3. And we already know this one, which is carbon dioxide, which has CO2 as the chemical formula. The next one is methane, and methane is a type of hydrocarbon. Okay, so methane is a type of hydrocarbon and has the chemical formula CH4. Okay, so we will look at methane a bit later on in the lesson. But yeah, so it's used as a fuel, and we'll look at it a bit later on in the lesson, and has the chemical formula CH4. So how many hydrogen atoms are there and how many carbon atoms are there in methane? So who can tell me the amount of, yeah, so 1 carbon, excellent. And how many hydrogen atoms are there? 4 hydrogen, well done, yes. Next, we have sulfur dioxide. Sulfur dioxide is an example of a greenhouse gas, and it has the formula CO2. No, sorry, SO2. And yeah, so that's sulfur dioxide. Again, sulfur dioxide, how many sulfur atoms are there and how many oxygen atoms are there? One sulfur, excellent, good. How many oxygen atoms are there? Two oxygen, well done, yes. So you guys are really getting this, which is good. So sulfur dioxide has one sulfur atom and two oxygen atoms. And then we already know about H2O, which is water, which has two hydrogens and one oxygen. Okay. So now we're going to look at the basics of a chemical reaction. Okay, so we said that compounds are when two or more elements are joined up together and they undergo something called a chemical reaction. So what exactly is these chemical reactions and how can we write them? So in a chemical reactions, you guys can think of it as having two different parts. Okay, so we have something called the reactants. Okay, and then we have something called the products. So the reactants are when you just putting things in and reacting together, reacting them together. So that really isn't just in the name. So reactants react together, and then those reactants will form the products. Okay, so it's just really simple as that. When it comes to chemical reactions, you have the reactants where you're putting things in and they will react together, they'll do their thing, and that the end of it, it will form the products. Okay, so when we write a chemical reaction, we will write the reactants on the left hand side and we will write the products on the right hand side. And we have to show that the reactants, is forming the products. So we would do an arrow in the middle so that to show that this is forming this. Okay, so this is the basic way that you write a chemical reaction. Okay, so now let's look at an example of a chemical reaction then. So we have iron. Okay, so we put some iron in a test tube and we also put sulfur in a test tube, and we are heating this, okay, using this equipment, which you guys have probably seen in your science lessons, in your labs at school. So who can tell me what this equipment is? What are we using to heat that iron and sulfur up? Bunsen burner, excellent, good. Yeah, so this is a Bunsen burner and we're gonna put it probably on the blue flame. So Bunsen burner has several different flames and we could put it on the blue flame and we will heat up iron and sulfur, okay? And then we will form iron sulfide, okay? So in this case, our reactants, okay, so our reactants in this chemical reaction will be iron plus sulfur, because iron and sulfur is what we're putting into the reaction, okay? And this is reacting together when we heat it up. This iron and sulfur are reacting together and it is forming the product, which is iron sulfide. Yeah, so this is forming the product iron sulfide. So this is just that in like a schematic, okay? So we have our reactants, which is the iron and sulfur, okay? So if we go back to our basic of our chemical reaction, we have on the left-hand side of the arrow, remember we have to show an arrow to show that we're forming the products from the reactants. So we have reactants on the left-hand side of the arrow, and we have the products on the right-hand side of the arrow. So we have the iron and sulfur, which are both reactants, forming our product of iron sulfide once we heat this up with our Bunsen burner, okay? So when we talk about chemical reactions, there is a concept that we have to understand, and that concept is called the conservation of mass. So what does that really mean? Okay, so that is really summarized very well in this sentence, okay? It means that the mass of the reactant, as in how much of the reactant you have, will always be the same as the mass of the product. Okay, so let's put some numbers into this to try and make sense of this, okay? So say in your science labs at school, you are, again, we're still sticking with our iron and sulfur and our Bunsen burner to make the iron sulfide. So you measure out 3 grams of iron, okay? So you've measured out 3 grams of iron and you have put that in to your test tube, okay? So this is showing our test tubes and we have put in 3 grams of iron. You measure that out really, really carefully and put in 3 grams of iron. Then you have also measured out 1 gram of sulfur and you have also put that into your test tube. Now you're going to be really careful with your safety goggles on and stuff, and you're going to heat it up using a Bunsen burner. And once you heat it up using a Bunsen burner, you will get our product, which is iron sulfide. And in theory, what you should get is 4 grams of iron sulfide, because when a chemical reaction happens, the mass of the reactants will always be the mass of the products. So if we do 3 plus 1, which is 4, so in theory, we should get 4 grams of iron sulfide. So if you were to heat this up, so once you've heated this up, and if you were to measure the product that you get in the end, so if you were to measure the amount of iron sulfide, you will get 4 grams of iron sulfide, because when we add the reactants together, which is the iron and the sulfur, so we already said that we put in 3 grams of iron and 1 gram of sulfur, at the end product, we will get 4 grams of the product, because of this rule of conservation of mass, that the mass of the reactants will always be the total mass of the product. Okay, so that is conservation of mass. Does everybody understand that? Are we okay with that? Maybe you write something in the chat. Yeah, okay, so we understand that, okay? Right, let's go on and look at, we're going to do a poll, okay? So what does the law of conservation of mass tell you? Does it tell you that the mass always stays the same between the reactants and the products, okay? Or does it say the mass goes up? Does it go down? Or it can go up or down? So we just did this. So does the law of conservation, what is it telling you? I'm going to relaunch the poll. Now, I want you guys to tell me what does the law of conservation of mass tell you? What is it telling you? I'm going to give you guys a couple more minutes so the others can answer as well. Okay. Some of you have answered. I'm going to end the poll. Yeah, so the conservation of mass is this rule that we're talking about here. Okay, this is the conservation of mass that we're talking about. This law that during a chemical reaction, the mass is always conserved, as in the amount will stay the same. So the right answer for this, which majority of you got it right, is A. Yes, so the conservation of mass is telling you that the mass will always stay the same. So the mass of the reactants added up together, so in our case, iron plus sulfur, where we had 3 grams of iron and 1 gram of sulfur, will always be the same as the product. And we got the product as iron sulfide. And we said that we will make, once we've heated it up with our Bunsen burner, we will make 4 grams of iron sulfide because of this law of conservation that tells us that mass of the reactants added up will always equal the total mass of the products. Okay, so good. Right, so that was chemical reactions. When we write these chemical equations down, we need to consider 3 different things, okay? So one thing is that you can write these as words, which is what we've been doing so far, right? So we said that iron plus sulfur is making iron sulfide, and we wrote that all out in words. So another example of a chemical reaction is the reaction between copper and oxygen, where you get copper oxide. Okay, so you can write that as a word equation. But what you can also do to kind of save time and so to kind of save time is write that as with chemical formulas. Okay, so the chemical formula for copper is Cu. The chemical formula for oxygen is O2, forming copper oxide, CuO. Okay, so if we go back to our basics of our chemical reaction, we can see that copper and oxygen, which is on the left-hand side, okay, which is on the left-hand side of the arrow, are the reactants in this chemical reaction. And copper oxide is the product of this reaction because it's on the right-hand side of the arrow. And we will know that whatever mass that we're putting of copper and oxygen, okay, so say if we have 2 grams of copper and 2 grams of oxygen, okay, the law of conservation will tell us that there should be 4 grams of the product, which is copper oxide, okay? So a thing we have to make sure is that this equation is balanced. So we'll look at that in later slides, how to balance equations, which is a really important skill to pick up in chemistry. So we'll look at that in detail in the next few slides. But yeah, we need to make sure that this is balanced for the law of conservation to make sense, right? So you can see here, there is 2 atoms of copper because we put a big 2 next to the copper. So you can see that there's 2 atoms of copper. There's also 2 atoms of oxygen. And this equation is balanced, this chemical reaction is balanced because we've got 2 copper and 2 oxygens. How do we know that? Because we put that big 2 next to the copper, okay? So we need to make sure we can write chemical reactions in words. We also need to make sure we can write them in chemical as a chemical formula and make sure it's also balanced, which is key, which we'll come back to. And next thing that we have to make sure is that we put state symbols, okay? So what does state symbols mean? State symbols is how the actual element is looking. So for example, we know that copper is a metal. So copper is what we call solid. Oxygen, so oxygen, we breathe in oxygen. So oxygen is a gas. And when we form copper oxide, the end product will also be a gas, okay? So there are several different state symbols that you need to keep in mind, okay? So we also said solid, so things like metals and stuff will be a solid. But bear in mind though, metals can also be liquid as well. So, but in most cases they will be solid. Another one is liquid, okay? So a liquid will show that in brackets with a L. Okay, so solid we show in small brackets, like just like that, small brackets with an S. So liquid, we could have water, we could have an example of an acid, HCl. Okay, so can any of you tell me what HCl is? What is HCl in the chat? Okay, so HCl is an example of a acid and is hydrochloric acid, okay? And we can also write that as a, we can also have the state symbol gas, so like oxygen or maybe CO2 is also a gas. Aqueous means in solution. So when something is dissolved in solution, so we can have a salt like calcium carbonate, for example, dissolved in a solution. So when that's dissolved in a solution, we say that's aqueous, and that is AQ in small brackets, okay? But the ones you will see most of is solid, liquid, and gas, okay? Right. So we talked about this law of conservation and saying that the mass of the reaction should always equal the mass of the products, right? So how do we make sure that happens? And that is by balancing the number of atoms on either side of the reaction. So the number of atoms of the reactant, which in this case is copper, should always, in this case, it's also copper and oxygen, sorry. Okay, so this is the reactants because it's on the left-hand side of the arrow, should always equal the number of atoms on the right hand, on the product, which is on the right hand side of the arrow. Okay, so is first of all, when you're trying to balance an equation, the first question you should ask yourself is it already balanced? Because there's no point of us trying to balance something that is already balanced. Okay, so you have to ask yourself, is this balanced? Well, how do we know whether it's balanced or not? Sorry, is there something in the chat? Okay, so it's not balanced, right? How do we know it's not balanced? We can write out the number of atoms on either side, okay? So on the left-hand side, which is, remember, the reactants, and the right-hand side. Okay, so how many copper atoms are there? On the left-hand side, there is 1. How many oxygen atoms are there? There is 2. On the product side, so copper oxide, in copper oxide, there's also 1 copper, but there is only 1 atom of oxygen. So we know the amount of reactants is not equaling the amount of products because there isn't the same number of atoms on each side. So we have to make this balanced, okay? So how do we make this balanced? Because we need to make sure that we have 2 of oxygen, okay? So we need to make sure there's 2 atoms of oxygen. So what we can do is times this by 2, okay? So we can't, one thing you need to remember with balancing equations is that you can't put a 2 here, okay? So you can't put the small number subscripts anyway. You can only put big numbers. So you can only put numbers at the beginning of the compound. You can't put a small 2. Okay, so if we want to make sure that there's 2 atoms of oxygen, we have to put a 2 up the front. Okay, so if we're putting 2 at the front, what does that mean for copper? Now that means, because when you put a big 2 at the end, at the start, sorry, we have 2 atoms of copper and also 2 atoms of oxygen, okay? So now we have 2 copper, 2 oxygen. So is this balanced? No, it's not balanced yet at this stage. Why not? Because we've now balanced oxygen. So oxygen has been balanced because there's 2 oxygens on the left-hand side and there's 2 oxygens on the right-hand side. However, now there is 2 oxygens. No, so there's 2 copper atoms on the right-hand side. So how do we balance this? We balance this by putting a big 2 at the front of the copper. So if you put big 2 in front of the copper, remember when you're putting big 2, anything at the start of a compound, you're timesing it, okay? So now we have 2 copper, okay? So we times that by 2. So now we have 2 copper and 2 oxygen atoms on the left-hand side, and we have 2 copper and 2 oxygens on the right-hand side. Okay, so does that make sense of how we balance things? So first we ask ourselves questions. I think there's a few in the chat. Yeah. Okay, excellent, good, yeah. So first we have to ask ourselves, is this equation balanced? If it's not balanced, you write down all the elements on the left-hand side plus the right-hand side, and you see which ones aren't balanced. And remember, you can't put small 2 anywhere or small numbers anywhere. You can only put big numbers at the right-hand side. Big numbers at the start of a compound, okay? So that is balancing. So we're going to look at a few examples. Okay, so that's that in like a schematic. We're going to look at a few examples. Okay, so the next one we're going to look at is magnesium plus HCl, which we already said is hydrochloric acid, okay, which forms magnesium chloride plus H2. Can anybody tell me what H2 is? What is H2? Why? Hydrogen. Yeah, so it's hydrogen gas, okay? H2 is hydrogen gas. So first we have to ask ourselves, is this top one, okay? Is this balanced? Okay, so is this balanced? No, it's not balanced. And how can we kind of figure that out if it's balanced or not? We just do our method of left-hand side, right-hand side. We have magnesium. There's one magnesium atom. There is one hydrogen atom. And there is one chlorine atom. On the right-hand side, we have one magnesium. We have one chlorine. No, sorry, we have two chlorine and we have two hydrogen. So no, it isn't balanced, okay? So what is imbalanced? Because magnesium is balanced, so we're okay with that. What is imbalanced is hydrogen and chlorine. So how can we make hydrogen and chlorine balanced? Well, if you put a 2 at the front of hydrogen and hydrochloric acid on the left-hand side, so we're putting 2 at the start, so we're going to times everything, okay? So we're going to times hydrogen and chlorine. So you have 2 hydrogen and 2 chlorine, okay? So now is it balanced? Yes, it is balanced because we still have one magnesium that's already been balanced, and we put that big 2 in front of HCl to make 2 hydrogen atoms and 2 chlorine atoms, which matches up with the right-hand side because we also have 2 magnesium. Sorry, we also have 2 chlorine and 2 hydrogens. Does that make sense? Does that make sense? Is that making sense? Yeah. Okay, good. Right. Let's have a look at another one, okay? So, is this balanced? I want you guys to tell me, is this balanced? So, is this balanced? No, it's not balanced. Okay, so how can we tell if it's not balanced or not? So we just do our method. We have the left-hand side elements. We have the right-hand side elements, okay? We have, what are the ones that we have on the left-hand side? We have hydrogen. So the reactants on the left-hand side, we have the hydrogen. So remember, when we're talking about left-hand side, we're talking about the reactants here, okay? And the products on the right-hand side. So we have hydrogen, 2 hydrogens, and 2 oxygens. On the right-hand side, we have 2 hydrogens, so that's balanced, but we only have 1 oxygen, okay? So how can we make sure there are 2 hydrogens, 2 oxygens on the left-hand side, on the product side of H2O? So how can we make sure there's 2 hydrogens? So what can we do? What are we thinking? What can we do here? Yeah, excellent. Yeah, so if we add a big 2 here, okay, we're adding a big 2 on the H2O, so there's 2 H2Os. Remember when we add big 2, we have to times everything by 2 for whichever whichever compound you're adding it to. So now we have 4 hydrogen atoms and 2 oxygen atoms, right? Okay, so now oxygen is balanced because we have 2 oxygens on the left, on the reactants, and we have 2 oxygens on the products. However, what is now not balanced? What is now not balanced is hydrogen, because if you look on the product side, we have 4 hydrogens and we only have 2 hydrogens. So how can we make that balanced? What are we thinking? How can we make that balanced? A big 2, yeah. So where can we put that big 2? In front of the H, yes, on the left-hand side, in front of the H, if we put a big, sorry, what's going on? What did I do? Okay, there we go. If we put a big 2 on the left hand, in front of the H2, we now have, because remember, we have to times it. So we have 4 hydrogens on the reactant side, 4 hydrogens on the product side, 2 oxygens on the reactant side, and 2 oxygens on the product side. Okay, so we have this. So now it is balanced. So do we understand that? Do we get that? Is that okay for everyone? So, yep, I got 1 yes. Any more yeses? Yep, good, excellent. So, yeah, good. We're going to have practice now, okay? So we're going to have practice of doing these equations, okay? So, okay, so this is going to be our first one. CH4 plus O2 makes carbon dioxide and water. I'm going to give you guys a minute. Can we try and balance this? First, I want you to tell me, is this balanced? If not, how can we balance it? Give you guys a couple of seconds to kind of figure that one out. And once you have, can you put that into the chat? How can we balance this chemical equation? What are we thinking? Guys, I just want to say, with the balancing equations, the best way to get better at it is just by practice. Okay, so you just have to practice. It's not balanced, excellent, good. So you just have to keep practicing, trying to balance equations, and you guys will get the hang of it. Okay, so how can we try and balance this then? Any ideas on how we can try and balance this? What are we thinking? How can we try and balance this? Any ideas? Are we all thinking? Okay, so let's work this out then. We have the reactants, or what we said, the left-hand side, okay? And we have the products, which we've said is the right-hand side, okay? So first step is to write down all the elements that we have, all the different atoms, okay? So we have 1 carbon, 4 hydrogens, and 2 oxygens. On the product side, or the right-hand side, we have 1 carbon. Okay, so we have, that's going to be hydrogen, okay. So we have 1 carbon, 2 hydrogens, and we have 3 oxygens. So from this, you can already tell that this is imbalanced, because we have 2 oxygens and 3 oxygens on the left-hand side, and 3 oxygens. Is somebody put? Okay, yeah, so yeah, excellent. Yeah, so you guys are getting the hang of this. You have 2 oxygens on the left-hand side and 3 oxygens on the right-hand side, and you have 4 hydrogens on the left-hand side, and then you have 2 hydrogens on the right-hand side. So which one is the easiest to kind of try and balance first will be the hydrogen, okay? So how can we try and do that? Well, we have 4 here and 2 here. So if we times this by 2, as in the H2O by 2, so we put a big 2 here, what do we get? Now we get 4 hydrogens, because we had to times, remember, when we are putting big 2s anywhere or big numbers, we're timesing the entire thing. So there are already 2 hydrogens here. So we're going to do 2 times 2, and now we have 4, okay? But that also means that now we have 2 oxygens here, okay? So we now have 4 oxygens because we've now times 2, because we had 1 oxygen here. So 1 times by 2 is now 2 oxygens. So overall, we now have 4 oxygens. So this number 3, I've just added the 2 oxygen here and 1 oxygen here, okay? So, but remember, we're just putting the big 2 in front of the H2O. And in H2O, there's only 1 oxygen. So that's why we're timesing the 1 times by 2 to get the 2 oxygens, okay? So if we add the 2 oxygens from the H2O, and then we already have the 2 oxygens of the carbon dioxide, we have 4 oxygens, okay? But now the oxygen is in balance because we only have 2 here and we have 4 on the other side. So if we times that by 2, we get 4 oxygens. So we're going to put big 2 here and we get 4 oxygens on the reactant side or the left-hand side. So now this is balanced because we have 1 carbon, 4 hydrogens that we've gotten by putting a big 2 on the H2O. And now we have 4 oxygens as well, because once we put the big 2 in front of the H2O, we now have had 2 oxygens on the H2O and 2 oxygens from the carbon dioxide, making 4 oxygens altogether. And so that means we have to put the big 2 in front of the oxygen to get 4 oxygens. So now all of this is balanced. Okay, does everybody understand that? I think a few of you put that into the chat. Yes, okay, excellent. Should we practice another one? So let's practice this one then. So first of all, is this balanced? If not, how can we balance it? After this one, we'll go on our break, and then we will do the last balancing equation after our break, okay? It's not balanced. Okay, so how can we try and balance this then? Any ideas on how we can try and balance this? Okay, so you're saying you can add big 2. So add a big 2 in front of the Al. Okay. So on the left-hand side. Okay, so when you say left-hand side, you just have to make sure which element, which compound or element you're talking about in particular, okay? So big 2 on the left-hand side is correct, but which element is it? So is it at the oxygen or is it at the compound of O2? Okay, Al, excellent, good, right. Okay, then what can we do? So is that balanced at this point? No, no, it's not. So what needs balancing? O2 needs balancing. Yeah, the oxygen needs balancing. So how can we try and balance this oxygen? Excellent, yes. So if we put a 3 here, what do we get? We get 3 oxygens, good. No, sorry, we get 6 oxygens. Okay. So does that mean now the oxygen is balanced yet? Does that mean, so we put the 6 here, so you put 4 in front of, yeah, okay, so we're gonna get there. So let's look at the oxygen now. Yeah, so you put the big 2 in front of the Al, the aluminum oxide. Okay, so now you have the oxygen balanced, okay, because now you have 2 times 3, which is 6 balanced. And so does that mean how many aluminium atoms do you have? Because now you have then add. Okay, so remember, you can't add 2, the small 2, which is a subscript, you can't add that in. That's one of the rules of balancing. You can't add small 2 anywhere, okay? You can only add big numbers in front of the element or the compound, okay? So somebody's saying 4, where are we putting the 4? In front of the aluminium, yeah? So now is this balanced? Okay, let's write that out. So you have 4 aluminium plus 3 O2 forming 2 Al2O3. So we have 4 aluminium, 6 oxygen. On the left-hand side, you have 4 aluminium on the right-hand side, because remember, 2 times by 2 is 4, and 2 times by 3 is 6. So this is balanced. Yeah, excellent. Okay, so hopefully you guys are getting that. There's one more balancing equations that I really want you guys to practice, but we're going to go on a break till 11 o'clock, and then we'll look at the next one, okay? So if you guys want to use the bathroom or get a drink, feel free. We'll start again at 11, okay? But really good work, guys. I really love the engagement today. It's really, really great to see, okay? So see you guys back at 11. All right. Okay. So we're going to do this one more practice of a balancing equation, and then we are going to move on to endothermic and exothermic reactions, okay? So I'm going to give you guys a couple of more seconds for this poll, but can you tell me which of these correct balanced equation is for the reaction of lithium with water? What are we thinking? You can take a bit longer to answer this because I really want you guys to, sorry, can everybody hear me okay? Can everyone hear me? Yes, okay, cool. Yeah, so you guys can take a little longer with this, but what is the, sorry, have I not launched the poll? Is that it? No, I have launched the poll. Okay, so what, this is the last balance equation question that we will be doing. Which is the right answer for this one then? Which is the balanced equation when you react lithium with water? What do we think? So it's lithium with water, okay? So we won't, yeah, so it's going to be lithium with water, all right? So if we just do process of elimination here, you can work this one out. You don't really have to even balance it in a sense, because when you do lithium plus H2O, we can't get sodium oxide, sodium hydroxide even, can we? So this is sodium hydroxide and Na is sodium, okay? Because we're not even reacting sodium here, are we? We're reacting lithium. The same goes for all of this. So all of this is actually wrong, okay? So the one we have left is lithium hydroxide. So is this balanced? Let's see. We can see that there's two lithium here. There is 2 times 2, so there's 4 hydrogen atoms. So we have 2 hydrogen atoms here and 2 hydrogen atoms here, so that's 4. And we have 1 oxygen. Sorry, we have 2 oxygen and we have 2 oxygen here. So that's 2 for oxygen. So yes, this one is completely balanced. Does that make sense for everyone? How we get this as the right answer for this? Yeah? Sorry, do we have any questions? Yeah, okay. So that will be the end of balancing equations. But like I said, with balancing equations, just practicing a ton of it can really, really help, okay? So that'll be the end for balancing equations. Now we're going to move on and look at chemical changes, okay? In particular, we're going to look at what is actually happening when a chemical reaction takes place, okay? So if you think about going back to our iron and sulfide, iron and sulfur, and then it forming iron sulfide, what actually is happening in a chemical reaction? So would be the bonds are being broken. So the bonds between iron and sulfur is being broken. Okay, so sulfur is being joined up, iron will also be joined up. So iron has the chemical formula Fe. So atoms of iron will be joined up with other atoms of iron. Same principle goes for sulfur. So what needs to happen for us to form Fe sulfur, iron sulfide, is that bonds between iron needs to be broken. Bonds between sulfur also needs to be broken. And we need to form new bonds between iron and sulfur. So in a chemical reaction, bonds are being broken within the reactants, and then new bonds are being formed within the products. Okay, so the principle is that breaking of these bonds requires energy. Okay, so if you guys think about that in a logical sense, so say if you had a stick, so this is my very poor drawing of a stick, and you wanted to break the stick in two, you have to put some arm strength, like you have to put some arm power into this, don't you, to break. So to say it's a really thick stick, you're going to require energy. It's going to require you to put in energy, put some arm power, show off your biceps to try and break this stick. So breaking of bonds is a similar principle. When you're breaking them, it requires you to put in energy. And when you're making these bonds, it releases that energy. Okay, so when you're making it, it releases it. Breaking bonds, just think of it as a stick. You're trying to break the stick, which requires you to put in the energy. So breaking of bonds requires energy. Okay, so we call that either endothermic or sorry, this is supposed to say exothermic reactions. Okay, so either endothermic or exothermic reactions. So the way you can remember that is by endo, bendo, so they both have B. Okay, so B is for breaking, so bendo, B, and breaking B. So you know that's endothermic reaction. And making, okay, so you think exo sounds similar to mexo. Mexo has an M, making has an M. So making bonds is exothermic, and breaking bonds is an endothermic reaction. Okay, so let's look at that in more detail here. So when you're breaking bonds or in an endothermic reaction, yeah, because we said endo sounds like bendo, they both have bendo and breaking both have B in it. So in a reaction, for new products to be formed, the bonds of the reactants need to be broken, like we just said, and that breaking of the bonds requires energy. So we think this is a stick, or maybe this is iron, with our case of iron sulfide. Forming iron sulfide, you break these bonds between the iron, and you just now have individual atoms of iron, okay? So this will need energy, all right? And then making bonds, okay, so let's say you're making iron and sulfur, will release that energy, okay? So that's what, and remember, making and mexo both have M in it, so it's exothermic reactions is where you're making bonds, which is releasing energy. Okay? Cool. Right. So if a reaction needs to be overall an exothermic reaction, okay, what that means is that we need to, when more new bonds are made, than bonds being broken, the energy released is greater than the energy that we're putting in, or the energy that is required. So this will be an overall exothermic reaction. Okay, so I'm going to repeat that because I really want you guys to get your head around this concept, okay? So when you're making new bonds, more than you're breaking new bonds, okay, the energy released, so the energy that you're putting out will be way more than the energy that is required to make those new, to break those bonds, because you're making more new bonds than you're breaking. So it will be an exothermic reaction. So can we think of any examples of exothermic reactions? Maybe put some into the chat. What are examples of exothermic reactions then? Any ideas on examples of exothermic reactions? It's okay if you don't, that's fine. Okay. Yeah, so examples of exothermic reactions are combustion, which we will look way more in detail after our second break, okay? Combustion and neutralization. Can anybody tell me what neutralization is? It's kind of a hard question, so I'll be impressed if you guys can get it. What is neutralization? What are we thinking? What do you think neutralization is? Any ideas? Okay, we have one in the chat. Let's see what we think. When alkali is mixed with an acid, excellent, yes. So when you mix an alkali with an acid, you're neutralizing it basically, and you will form water, and water has the pH of 7. So this is a completely different topic, but this process of mixing an acid with an alkali is an exothermic reaction, okay? And because exothermic reactions, you're releasing energy, right? You're releasing energy. The temperature of the surroundings, okay? Temperature of the surroundings will increase. And what is a good way to remember that is by thinking, so a good way to remember that is by thinking exo, you exit out. Okay, so you think exo, you're exiting out heat. Okay, so the temperature, so you're giving out heat, therefore the temperature is going up. So in exothermic reactions, and two examples of exothermic reactions are combustion, when you're burning something in oxygen, so that's what combustion is, and neutralization. And remember, in exothermic reactions, you're making more new bonds than you're breaking, and that is releasing energy, and therefore the temperature of the surroundings will increase. So mexo, making, they both have M, so exo is making new bonds, which is releasing energy, okay? And exothermic sounds like exit. Sorry, it sounds like exo, exit. So you're exiting thermic energy or just heat. Therefore, the temperature will go up. Yeah. Does that make sense for everyone? Do we understand exothermic reactions? Do we understand what exothermic reactions are? Do we get examples of exothermic reactions? Yeah? All of that making sense? Okay, so now let's move on to endothermic reactions then. So we already said endo sounds like bendo, bendo and breaking both have a B in it. So endothermic reactions are breaking, is when you're breaking bonds. So endothermic reactions is basically opposite. So what happens in endothermic reactions is basically the opposite of what's happening in a exothermic reaction. So when you're breaking more bonds, then you are making, so when you break more bonds, then you're making more bonds, the energy needed is more. Because remember with our stick example, when you're breaking that stick, you need to put energy in. So the more energy is needed, so then you're giving out. So more energy is needed, then you're releasing that energy. Okay, so this is endothermic reaction. When more bonds are broken than bonds being made, the energy you need to break those bonds are way more than the energy you're giving out, which is what endothermic reactions are. Okay, so can anyone think of examples of endothermic reactions? Does anyone know any examples? What are we thinking? What are examples of endothermic reactions? What are any examples of endothermic reactions? Okay, that's fine. So examples of endothermic reactions are photosynthesis, okay, and thermal decomposition. So breaking something down by heat are examples of endothermic reactions. What is photosynthesis? Can someone tell me what photosynthesis is? Any ideas on what photosynthesis is? What is photosynthesis? I wouldn't necessarily say this is chemistry, but yeah, exactly. So it's to do with plants, and it's when plants basically make their food. Yeah. So that is photosynthesis, and photosynthesis is an example of an endothermic reaction. Also, breaking something down by heat is also an example of thermal decomposition. That's basically what that means. Thermal means heat, and decomposition means breaking something down. Okay. So both of these are examples of endothermic reactions. And so what is happening with the temperature then in endothermic reactions? Well, what happens is the temperature of the surroundings will decrease, because if we remember what endothermic reactions are, we are breaking more bonds than you're making. Okay, so you're breaking more bonds. So what does breaking bonds require? It requires you to put in energy. Okay, so if you think of putting in that energy, so endo has both of them N, so you're putting in energy. So the temperature of that surrounding will decrease because you had to take that energy in. So you had to take that heat in. So in endothermic reactions, the temperature of the surroundings will go down. So exothermic, temperature goes up. Endothermic, temperature goes down. Exothermic, you give out, exit heat. So that's why the temperature of the surroundings is going up. Endothermic, you're taking in heat. So temperature of the surroundings goes down. Does that make sense for everyone? Yeah, so it's making sense. So we understand what endothermic reactions are. We understand what exothermic reactions are. We know the examples of both. So examples of endothermic reactions are photosynthesis and thermal decomposition. Examples of exothermic are neutralization, when you mix an acid and an alkali to make something that has a pH of 7. And combustion. And we understand that exothermic reactions temperature is going up because you're exiting the heat out. So heat goes out, temperature goes up. In endothermic, you are putting in, you're taking in the heat, so the temperature of the surroundings will decrease. Okay, right. Let's have another poll then. So when we are breaking bonds in a chemical reaction, is the energy being released or is it being absorbed? So I'm going to relaunch this poll. What do we think? When we're breaking, remember, we are breaking. So think of the stick and think of the stick. So when you're breaking that stick, what does that require for you to? Yeah, so when you're breaking that stick, you are putting in that heat, okay? Sorry, you're putting in that energy. So energy is being absorbed when you're breaking those bonds. Energy is being absorbed because energy, when you're breaking bonds, it requires you to put that heat in. And then when you make the new bonds, so in, when you're making new bonds, in exothermic reactions, energy is being released, okay? So when you break bonds, what is breaking bonds? What is that reaction called? Endothermic. In endothermic, you are absorbing that energy to try and break the bonds, okay? So the wording can get a bit confusing, but in endothermic, you absorb the heat to try and break the bonds. Yeah? Does that make sense? So the right answer here is energy is being absorbed. Yeah? Or are we confused? Does that make sense as to when we break bonds in chemical reactions, whether energy is being absorbed or whether it's being released? Do we understand this question? It's kind of a harder question because the wording is a bit different, but do we get it? Yeah? No? Yes, we get it. Okay. Yeah. Okay, cool. So now we're gonna have a few more questions before we go on to collision theory. And so the first one, in exothermic reactions, does the temperature go up or the temperature goes down? What are we thinking? exothermic reactions. What is happening to the temperature? So write your answers in the chat. Oops. In exothermic reactions, does the temperature go up or does the temperature go down? So we're talking about the temperature of the surroundings, okay? What do we think? Okay, so a couple of you put down. Remember, exothermic reactions, we are exiting the heat. So we're exiting that heat into the surroundings. Surroundings, okay? So the temperature of the surroundings will go up, won't it? Because we said exo is you're releasing. Exothermic reactions is when you're making bonds, and that is releases energy. And therefore, it is releasing that heat, exo, and therefore the temperature of the surroundings will go up. Yeah? Does that, okay, yeah, does that make sense? It can get a bit confusing. But in exothermic, just think exo, you're exiting heat out, temperature will go up. Endo, heat comes in. So endo and in have both got N in it. Endo, heat in. So heat is coming into the reaction. So the surrounding temperature will go down. Okay, so when we talk about temperature here, we're talking about the surrounding temperature. So in other words, where are we getting the heat from? So the heat is going to be like the energy for this. So temperature here is also the surroundings. So in endothermic reactions, what's going on with the temperature then? An endothermic temperature will go down. Yeah, temperature will go down in endothermic reactions. Yeah, so does that make sense? As to what's happening with the temperature with exothermic and endothermic? Yes, okay. Now, what's two examples of exothermic reactions then? We talked about this, exothermic reactions. What are two examples? Neutralization, excellent, good. What's another example? Combustion, yeah, excellent, good. So now, well, sorry, exothermic, yeah. Endothermic reactions, what are two examples of endothermic reactions then? Photosynthesis, excellent. And what's the other one? Thermal decomposition, excellent, good. Yeah, so hopefully you guys understand that. If you have any questions, just put it into the chat. But yeah, so that's exothermic and endothermic reactions. There is another concept that we have to get our head around when we're talking about chemical reactions, and that is the concept of the collision theory, okay? So if we want any reaction to take place, we need the particles. So if we go back to the example of iron and sulfur, if we want any of this to react together to form iron sulfide, okay, we need the particles to collide. So if we say the blue is iron, okay, so the blue is iron and the red is sulfur, we need the atoms of iron and sulfur to react together. So we need them to collide with each other with enough energy. So they need to collide with enough force or enough energy. And that enough energy is called the activation energy. Okay, so once they collide with each other with enough energy or with activation energy, that's what, so we know then that the chemical reaction will happen. Okay, so that is the collision theory. They need to collide with each other with enough activation energy, and the more energy the particles will have, the more likely the collisions will be successful. So if you have that more energy and you have that actual activation energy, when they do actually collide, that means they will all react together and the collision will be successful. And so that's a concept that we have to understand with any chemical reaction, that the particles need to collide with activation energy for that collision and that reaction to be successful, okay? So there are several things that kind of increase the chance of that collision happening, or we call that the rate of reaction, anything that can affect how quickly the particles collide and form the product, okay? So that's what we mean by the rate of reaction. And there are several different things that can increase the rate of reaction. Before we go on to look at them, do we know which ones they are? Any guesses on anything that can increase the rate of reaction? It's okay if you guys don't know, we'll be looking at it just now. Okay, so there are 4 things. The temperature, excellent, good. Yes, temperature is one of them. So there are 4 things that can affect and increase the rate of reaction. The first one is concentration. The next one is pressure. And somebody already mentioned temperature, so good. Yes, one of them is temperature. And something called the catalyst. Okay, so how can what do we mean? First of all, we need to understand what we mean by increasing the concentration. So, like we said, if we said that the blue one is iron and the red one is sulfur, okay, if you look on this schematic, you can see this is box A, box B. So you're going to imagine that this is your test tube and you're going to heat it, you're heating this up, okay? So in one version where you're doing it, you have iron and you have sulfur. But in your next, so for maybe your friend's test tube, they've put more sulfur in because you can see more atoms of sulfur because we said that the red ones are sulfur, right? So you have iron and the red ones are sulfur. You can see there's only 2 atoms of sulfur in here, but they've put way more sulfur in box in their one or in box B. So this is what we mean by increasing the concentration because we have now increased the concentration of sulfur. Okay, so let's have a look at what that does in terms of the rate of reaction. So when we increase it, we know we're increasing the rate of reaction. So the rate of reaction is now going up. Okay, so how is that happening then? So we said the concentration increases, the rate of reaction increases as well. So when we increase the concentration, we have many more of these sulfur molecules in that given volume. So this is a really important concept to understand. We're keeping the volume the same. So what does that mean? We have the same size test tube. So in this case, you can see that if that was 1 centimeter, which is not, but like say if that was 1 and that was 1, the volume of this is the same as and this is also 1 and this is 1. So the volume of this is the same, and we're keeping that in our practical sense, we're keeping the test tube the same. So in a given volume, there's more amount, okay, so that there's the amount of molecules in that given volume has increased. This means that there's more likely that there will be a successful collision. Why is that? Because when you put more things in like the same space, we have more of these sulfur atoms. So this and this, so the iron and the sulfur, is more likely that the iron and the sulfur will collide together. This iron and the sulfur can collide together. Yeah, and they probably collide with this one as well. Whereas in this case, there's only 2 sulfur atoms in this given space, right? So the chances are this can collide together, and that can collide together. But then, you know, there isn't like we have more sulfur atoms here for it to be colliding together like this. So this one and this one. So that means there is more chance that there can be successful collisions. Okay, so when you increase the concentration, you're increasing the rate. That means as the amount of molecules in that given volume also increases. So therefore, there are more likely to be successful collision just for the fact that there are more of that sulfur atoms in that given space. As a result, the rate of reaction will increase. So you need to say that there are successful collisions and that the amount of molecules in that given volume has increased. That's an important thing to remember when you're talking about the increase in the concentration, how the increase in concentration can affect your rate of reaction, okay? So that's concentration. So now we're going to increase the pressure. Okay, so what do we mean by increasing pressure? So in the concentration one, we've just increased the amount of each substance. Okay, so we increase the amount of sulfur. In this case, we're going to make the test tube or the box in the schematic sense, we're going to make the box smaller. So these are all way closer together and we have increased the pressure. Okay, so in this box, the iron and the sulfur have way more space to move around, meaning that the collisions, there's less chance of them to colliding with each other because they have way more space, they're moving around way more. Whereas in this case, we've decreased the space in the box. So you can clearly see now that these are way closer together and they have less space to move around, meaning there is a higher chance that these two will collide with enough activation energy. Remember, because we need, for successful collision, we need them to collide with enough activation energy. So there is more chance that these will now collide with enough activation energy and therefore have a successful collision. Okay, so how can we write that in words? Okay, so we've said that as the pressure increases, okay, so we're increasing the pressure here by making the box smaller. The pressure increases, there are more molecules in a given space. So what you need to remember here is in this box and in this box, the same number of molecules, because we're not talking about the concentration now, we're talking about the pressure. However, this box is smaller, therefore they're all closer together, yeah? So they're closer together. There are more molecules in that given space. So there's more frequent collisions. There's more chance that these can collide together more. And this means that it makes it more likely that they will collide with and there will be successful collisions, meaning that they will collide with activation energy. Therefore, the rate of reaction increases. Yeah? Does that make sense? How the pressure can influence the rate of reaction? Do we understand that? Any questions? Yes, got it. Cool. Right, let's move on to the next one then, which is temperature. Okay. So how does temperature? So the person who told me about temperature, having the rate, increase in the rate of reaction, how do you think the temperature can influence it? So can you maybe give me an explanation for it? What are we thinking? So a few points I'll give you guys a clue to remember is that, remember, these needs to happen with, for it to be a successful collision, it needs to happen with a activation energy. So what are we thinking? Heat increases, yeah, it gives them more energy. Yeah, so these are all good points, okay? So we're increasing the temperature now. So in the case of your test tube, you're going to just change the flame because that will increase the temperature or heat it for longer. Either way, it will work. So you're increasing temperature. What is going on here then? So you guys have all said good points, okay? When you increase the temperature, what is happening is that the particles will gain more energy. When they gain more energy, they get excited, what we call excited. And that means that the more molecules will have energy that meet the activation energy. Because remember, the activation energy is the minimum amount of energy that is required for it to be a successful collision, and therefore for the thing to actually chemically react. Okay, so when you have more energy, because you're heating it more, you're getting the particles excited, the particles gain more energy, that means there will be more of those molecules that will have the energy level that meets the activation energy or the minimum amount of energy that's required for that successful collision. So therefore, in fact, there'll just be more successful collision. So as a result, when you increase temperature, you're increasing the rate of reaction. Yeah? Do we get that? Yeah, so this one is warmer because the temperature is higher, and you can see they are colliding with enough activation energy there. Okay, so that is increasing the temperature. So Right, so there should be, okay, so the next one is the catalyst. Okay, so catalysts are chemical substances that speed up the rate of reaction. And they do that, and the thing, really cool thing about catalysts is that they won't be used up or they won't be changed in the reaction, okay? So we already talked about concentration, the pressure, and the temperature. Catalyst is the fourth thing that increases the rate of reaction. And it's something that you can just add into reactions and you can keep reusing it because it won't be used up in the reaction, or it won't affect any of the products or the reactants of the reaction, and it won't be changed. And it will just, the way the catalyst works is by, it provides an alternate pathway where you have lower activation energy. So you only require lower activation energy for there to be a successful collision. So that's how the catalyst influences a reaction, because it provides an alternate pathway with a lower activation energy. Therefore, we have more successful collisions. They won't be used up or changed, so they're really, really useful to have in reactions, and something that is used like in industrial levels. And an example of that is when you're making ammonia. So remember, we said ammonia. What was the chemical formula for ammonia? Does anyone remember? We mentioned it at the start. We talked about ammonia. Right, the NH3, excellent, good. So ammonia has the chemical formula NH3, and and in the process of making ammonia, we use iron as a catalyst. So you react nitrogen and hydrogen, you add iron, and it makes the process way quicker. And that process is called the Haber process, okay? Which you don't need to know too much detail about now, but you might do if you, when you get to GCSE or A-level level, okay? So, and that is catalyst. An important other concept to know about catalyst is that they're very specific. So you can't use iron in any other reaction as a catalyst. You can only use iron in the Haber process to make ammonia. They only work on certain reactions under certain conditions as well, okay? So you have concentration, you have pressure, you have temperature, and you have catalyst, all involved in increasing, or it can decrease. So if you decrease the concentration, obviously the opposite happens. There'll be less molecules in that given volume, and you will have slower rate of reaction. Same principle goes for pressure and temperature and catalyst. If you don't have a catalyst, then you won't have the quicker process. But all of these four things increase the rate of reaction. And you can manipulate all four of these to try and make a process, so like Haber process, a more like time and money effective process, basically. And they do that in chemical when you do chemical reactions at an industrial level, okay? So that is endothermic. So that's the different factors that affect the rate of reaction. So we also looked at endothermic and difference between endothermic and exothermic reactions. Now we're going to look at something called enthalpy diagram. So enthalpy, just to make our lives easier, it just means energy. Enthalpy means energy, okay? So we said there are exothermic reactions and we said there are endothermic reactions. You can show whether it's an exothermic reaction or an endothermic reaction on an enthalpy diagram or an energy diagram. So enthalpy change just means energy change. And progress of reaction is just talking about the time, okay? So you can show whether this is an exothermic or an endothermic reaction by doing this kind of diagram, okay? So what happens is you put the reactants and the energy level of the reactants, and then you put the products, which is the energy level of the product. And what this diagram is basically showing you is the change in the energy of the reactants and a change in the energy of the products. And this arrow here, okay, this arrow here represents something we already talked about, which is activation energy. What was activation energy? Can somebody tell me what activation energy was? What was activation energy? What was activation energy? Do you remember? Any ideas? So activation energy does have to do with the rate of reaction, but what else was activation energy? So activation energy, remember, is the minimum amount of energy. So minimum amount of energy that is required for the particles to be, sorry, no, I did something. Okay, what do I do? No, okay, okay. Minimum amount of energy that is needed for a successful collision. So two particles need to react, need to collide together with this much activation energy, so a minimum amount of energy for there to be to be a successful collision. So this arrow here in an enthalpy diagram, this arrow here is showing activation energy. And then this whole thing will be showing the overall energy change. And this diagram is showing as a exothermic reaction. And why is it showing as an exothermic reaction? It's showing as an exothermic reaction because the reactants have more energy than the products. And we already said in exothermic reactions, you release energy, don't you? You release energy in exothermic reactions because exo, exit. So you're giving out that energy to your surroundings. And we already said, what does that mean? The surrounding temperature will go up and the products itself will have lower energy. Okay? So the reactants have more energy than the products. Therefore, this is showing an exothermic reaction. Yeah? Does that make sense? Does that make sense for everyone? Any questions on that? Yeah? Okay, good. So this diagram is showing exothermic reaction. And we can do similar principle for endothermic reactions. Okay, so if we look at endothermic reactions, you can see that you have the reactants, you have the products, so the energy level of the reactants, the energy level of the products. You have this arrow here, which is showing us the activation energy, which we already concluded is the minimum amount of energy that particles need to collide with in order for it to be a successful collision and actually have the chemical reaction happen. Okay, and then you have the overall energy change. Here you have the overall energy change. Okay, so in this case, it is showing an endothermic reaction. How is it showing an endothermic reaction? It's showing endothermic reactions because the products have more energy. So the products is higher up on this graph than the reactants. So the products have more energy than the reactants. And remember, we said endo, in, yeah? Endo both have N in it. So you're taking in that energy because you're absorbing energy, you're taking and absorbing energy because taking in and absorbing energy requires, because you need energy to break bonds. So say if we're talking about iron, an iron, if you wanted to break that bond between iron and iron, you need energy. So you're taking in energy, you're absorbing energy to break this bond, and the temperature of the surroundings will decrease. But the products itself will have higher energy than the reactants. Therefore, overall, this is showing an endothermic reaction. Okay? Does that make sense? Is that making sense for everyone? Yes? Yeah? Okay. So enthalpy diagram. So these enthalpy diagrams are one of the kind of, it's harder to understand. So if you guys have any questions, just put it in the chat, okay? But, okay, so we're gonna move on and look at some exam questions now, okay? So we're gonna look at this exam question and then I'll give you guys a break because we've looked at looked at quite a few things today, so I'll give you guys a break. So let's look at this question. In lightning, the temperature can reach up to 30,000. This causes nitrogen and oxygen in the air to react, producing nitrogen oxide. And this reaction has high activation energy and is endothermic. Nitrogen and oxygen in the air do not react easily. What makes nitrogen and oxygen react during the thunderstorm then? What do we think? What is making, because when you think about normally without the lightning, the nitrogen and oxygen doesn't react together. So what is happening in the lightning that is providing this energy? Okay, I want you guys to expand a bit. Okay, any more ideas? What is happening in the temperature in lightning than in normal? What's the difference? If there wasn't lightning and then there was lightning, the temperature is really high, isn't it? So, sorry, too many zeros. So in lightning, you can get temperatures high as 30,000, can't you? That's what it's saying here, isn't it? It can reach up to 30,000. So it's that high temperature that's making, so the high temperature is providing that energy for it to be, for the nitrogen and oxygen. So what makes the nitrogen and oxygen react during the thunderstorms is the high temperature provided by the electricity or provided by that lightning. The high temperature from the lightning is allowing nitrogen and oxygen to react together. Yeah, does that make sense? So you can't just say it's energy, you have to be quite specific. So you have to say the high energy or the electricity that's coming from the lightning, and that allows the lightning or the heat and makes the nitrogen and oxygen react together. Yeah, does that make sense? Couple more in the chat. Yes, does that make sense? Okay. We're gonna go on a break. And when we come back from the break, we will look at some more exam practice, and then we will look at combustion and the fire triangle and stuff like that. But if we say we go on break till 12, and then we will look at the other stuff, okay? So see you guys in about 12 minutes, okay? So get a drink, use the bathroom, whatever you need to do, okay? I'll see you guys at 12. All right, everyone. I hope everyone's back from their break. We're going to start up again doing the last few bits of these exam questions before we move on to combustion and thermal decomposition, stuff like that. So the next question that we have is, during a thunderstorm, lightning strikes the Eiffel Tower. Complete the word equation for the reaction with nitrogen with oxygen. So we want a word equation here. So what do we think the answer to this question is? Write your answers in the chat. So remember, we talked about the fact that okay, so nitrogen plus oxygen, so those are our reactants. Yeah, and then our product will be equals nitrogen oxide. Excellent, good, yeah. So our product will be nitrogen oxide. Okay, so in this one, we just want the word equation. So that's, they'd be nice with us for this one. And remember, nitrogen and oxygen are our reactants on the left-hand side of the arrow. And nitrogen oxide, which is our products, so nitrogen oxide is our product. So in this case, you can give nitrogen oxide, nitrogen monoxide. Both of those would be correct. Excellent. So next question. So in an endothermic reaction, energy is taken in from the surroundings. Draw a ring around the correct answer to complete the sentence, okay? Sorry. In an endothermic reaction, the energy needed to break existing bonds is it less than, more than, the same as the energy released from forming new bonds? So we're talking about endothermic here, okay? So what do we think? Which one is it? What do we think? What's the answer? Is it less than or more than? Endothermic, so we're breaking bonds. And breaking bonds requires energy, okay? So in endothermic reaction, breaking bonds, the energy needed to break bonds is more than energy released from forming new bonds. Okay, do we all remember that, or are we confused? Do we have any questions? Do we get that? So in an endothermic reaction, the energy needed to break existing bonds is more than the energy that's required to forming those new bonds, okay? So if we're all a bit confused on that, we can go back to the slide where we talked about it, which is, sorry, which I believe is this one. No, I don't want to enter, sorry. Okay, which is this one. So remember, endothermic, endo, bendo has B, so breaking. That's how we can figure out that endothermic reactions is breaking bonds. So when more bonds are being broken than the bonds that are being made, the energy needed is more than the energy that is given out. Okay, because remember, breaking bonds requires you to put in that energy. So you will take in that energy from the environment. That's why the temperature decreases, remember, of the surroundings. Yeah? So if we go back to the question, with this topic, the wording of the questions can get a little confusing. So just with more practice, you'll be okay with it. So yeah. So in this case, in endothermic reactions, the energy needed to break those existing bonds will be more than the energy that's released from forming new bonds. Does that make sense for everyone? Yeah? Maybe put something in the chat just to let me know that you're all okay with it. Yes, okay. Okay, good. Next question. So this is, again, like I talked about, the enthalpy diagrams or the energy diagrams, okay? So the energy level diagram for this reaction is shown. which energy change, so A, B, C, is representing activation energy? Whoops, okay, so which energy is showing activation energy? It will be B, okay? It's B, sorry, the answer is already up here. So it is B that is showing the activation energy, okay? How do we know it's B? Because if we go back to our previous enthalpy diagrams here, right? So this part here is the activation energy. And can anyone tell me what the activation energy is? What was the activation energy? Come on, guys. It's the last bit. What is the activation energy? Anyone remember? Okay, so remember, activation energy was the minimum amount of energy you need for the part. So the particles requires this minimum amount of energy for it to be a successful collision. Okay? So B is the right answer for this one, activation energy. Okay? Next question then. Which energy change, A, B, or C, is showing that this is an endothermic reaction? So what do we think? Which reaction is it? Which letter is showing that this is actually an endothermic reaction? Yeah, C. Excellent. Good. So C is the right answer for this one. How do we know? Because remember, we already said this is an endothermic reaction. Nitrogen and oxygen are our reactants in this case. Yeah, so this is same as our enthalpy diagram that we showed in the earlier slides. They've just put, instead of reactants, they've actually just given examples of reactants, and they've just given examples of products as well. So nitrogen oxide is the product, and nitrogen and oxygen is the reactants. So in this case, the endothermic reaction, nitrogen and oxygen, which is the reactants, have lower energy than nitrogen oxide. So the products have more energy because the products have taken in energy. The products have taken in energy, and the temperature of the surroundings have actually, so temperature of their surroundings have gone down, and that energy is being taken in by the products. So energy, the products have more energy, and that arrow that shows that is C. So this is the correct answer. So C is the correct answer, and it's showing endothermic reactions. Okay, right. So now we're going to move on to combustion, and combustion we looked at, and we said that it was an example of exothermic reactions. Okay, so what does combustion actually mean? It just means burning. But the important thing to remember with combustion is that you're burning something, and also you're reacting it with oxygen. So when you burn something with oxygen, that is what we mean by combustion. So combustion is burn with oxygen. And when you burn it with oxygen, it's an exothermic reaction, meaning that heat will be released. Okay, heat is being released. Therefore, what's going to happen? The temperature will go up for the surroundings, won't it? Because it's an exothermic reaction. So that's what combustion is, burning with oxygen, which is an exothermic reaction. Okay? So these are all some examples of combustion. So you have lighting a match here, which is literally the definition, which you're burning that with oxygen. You have so petrol. So when you put petrol in the car, so it's not to say fireworks, it's supposed to say petrol. When you put petrol in the car, that is burning it. You're going to burn it with oxygen. So we will look at that different types of fuels in a second. And then fireworks is also an example of combustion because you're burning it with oxygen, and that fireworks looks really pretty, right? Okay, so when you need to burn something and make a fire, basically, you need 3 different elements to it, okay? So this is known as the fire triangle, okay? So the three elements you need in it is oxygen, and you need heat, and you need the fuel itself. Okay, so if one of these is missing, you won't be able to make a fire. So if oxygen is missing, you won't have a fire. If the heat is missing, you won't have a fire. If you don't have any fuel, you won't have a fire. So you need all three aspects of this triangle to make a fire. Okay, so this can come in useful when you're thinking of trying to put the fire out. So I'm sure we've all had examples of somebody burning toast at school, and the fire engine comes, and there's everybody has to go outside, fire alarm, fire engine comes, yeah, the whole shebang. So we can apply this principle when you're trying to actually remove that fire. So how can we try and get rid of oxygen? So there's a fire in school, and you try and get rid of the oxygen, or you need to try and basically remove one of the elements of the fire triangle. Okay, so you want to try and remove one of the elements of the fire triangle, and the first one you want to try and get rid of is oxygen. So we know there could be fire blankets. If you see loads of smoke coming from a toaster, for example, we have fire extinguishers. Okay, so the principle of how fire extinguishers work is that fire extinguishers actually have the supply of CO2. So you're actually replacing that oxygen, because remember, you have oxygen in the atmosphere. You're replacing that oxygen with the CO2 instead. So you're breaking one aspect of the fire triangle. Okay, so you can use these methods if it's oil fires or chip fan fires, electrical fires. So if you have some fire wires that are kind of heated up and it's causing like some smoke or something like that, you can use fire blankets or CO2 extinguishers. So that's how you get rid of one aspect of the fire triangle, which is oxygen. Next thing that you want to try and get rid of maybe will be the heat source itself. So you can do that just by throwing some water on it. So if there was like a really big fire, like a house fire or wood fire or paper fire or something like that, where you can see the physical flame and it's a really, really big fire, what you'll often see is the fire engine comes and they will start trying to cool it down with just a big hose of water, and they will just try and cool it down and just put water on it and remove the heat. And like I said, once you remove one of the heat, which is removing one aspect of the fire triangle, you will be you can try and put the fire out when you're trying to remove one aspect of the fire triangle, which is the heat, by just putting water on it. Another one is the fuel. So we're going to look at examples of fuels in a second, but you can try and put fire break. So this is really helpful in the case of forest fires as well. You can put fire breaks, and that will break that aspect of the fire triangle and try and put out the fire. So this is a really good application of how the science that we know, we're putting that in real life and actually using it for really useful things like putting out fires. Okay. So now we're going to look at examples of fuel then, right? So the fuel that we use is called hydrocarbons, okay? So hydrocarbons are examples of something we call fossil fuels, okay? So hydrocarbons is fossil fuels, and hydrocarbons, it's self-explanatory, it's in the word, consists of atoms of hydrogen and atoms of carbon. So they're made up of hydrogen and carbon. And you can use these hydrocarbons when it comes to combustion to try and have complete combustion or incomplete combustion. So we'll look at the difference of that in a bit. But the examples of hydrocarbons are methane, ethane, propane, butane, loads of different examples. And the difference between, so the suffix, so the prefix is the one that's kind of differentiating them basically. And that just depends on the number of carbon atoms there are in that particular hydrocarbon. So methane has 1 carbon atom, okay, and has the formula CH4. Ethane will have 2 carbon atoms, and that will have, sorry, okay, so ethane will have 2 carbon atoms. Okay, so ethane will have 2 carbon atoms and will have C2, okay? Right, so like I said, combustion can either be complete or incomplete. So let's look at the difference between complete combustion and incomplete combustion, shall we? So what's happening in complete combustion then? Okay, so what's happening in complete combustion? So in complete combustion, we already said combustion is, what was combustion? What did we say, like the definition of combustion was? Do you remember? What was the definition for combustion? Yeah, so you're burning. What are you burning with? What do you remember? What were you burning with? Burning with energy. Yes, what else were we burning with? Oxygen. Excellent, good, yeah. So combustion is when you burn something with oxygen. Remember our fire triangle? 4 aspects of our fire triangle, 3 aspects of our fire triangle. What were the 3 aspects of our fire triangle? Oxygen, fuel. And what was the last aspect of our fire triangle? Heat. Excellent, good, yeah. So that was the 3 aspects of our fire triangle, okay? So you had heat, oxygen, fuel. Sorry, fuel. Okay, so combustion is already burning with oxygen. In complete combustion, what you get is that there is enough oxygen, so there's plenty amounts of oxygen, and the fuel will react fully with that oxygen, and it will provide carbon dioxide and water. Okay, so that is complete combustion when there's loads amounts of oxygen and the fuel that you're using. So in this case, we're going to say the fuel that we're using is methane. So what was methane an example of? CH4. What was methane an example of? What was methane an example of? Do we remember? Okay, so methane is a fuel, but we said methane is an example of a particular type of fuel. What kind of fuel was it? Fossil fuel. So methane is an example of fossil fuel. It's also what class of, so remember methane, CH4, has carbon and hydrogen in it. Therefore, it is a hydrocarbon. Do you remember that? Hydrocarbon? We could use hydrocarbons as fuel in combustion. Yeah? Does that ring a bell, everybody? Yes, okay, good, right. So we're using methane, and when we react methane with complete oxygen, you'll get CO2 plus H2O. Okay, so we are going to try and balance this. So this is the equation, chemical formula for this reaction. We're going to bring in our balancing equation skills, and we're going to first figure out, is it balanced? If not, how can we try and balance it? So I want some ideas on the chat on how we can try and balance this. I'm just going to write this in word equation. So you have methane with oxygen forming carbon dioxide. Okay, I see there are chat. Okay, So that is the word equation for it. Okay, so first of all, is this balanced, guys? It's not balanced. No, it's not balanced. So how can we try and balance it? Any ideas? So remember, you can only add things. You can't take anything away when you're trying to balance. You can only add things on. And we have the left-hand side. Remember, we had the left-hand side, we had the right-hand side. So maybe you get a piece of paper and try and figure this out, and then put your answer in the chat. I'm just going to remind you guys of a few rules of balancing equations. You can only add a big letter, big number in front. You can't add any small numbers. There has to be the same amount of atoms on either side. And when you're adding big numbers, that means you have to times that big number by everything. Okay, so we have few suggestions. So on the right side, okay, add 2 in front of the H2O. Okay. Because it's H4 on the left. Excellent, good, right. So what does that mean now for the oxygen then? So now we have 4 hydrogens on here, 4 hydrogens on here. Okay, so is this balanced now? No. Okay, so what else needs to be balanced? The oxygen molecule needs to be balanced as well, because the oxygen isn't balanced right now, is it? So how can we, yeah, the oxygen needs to be balanced. Okay, so how can we try and balance the oxygen? Because now how many oxygen molecules, how many oxygen atoms do we have on the right hand side, and how many do we have on the left hand side then? Or how many do we have on the products? How many do we have on the reactants? Okay, so we have two on the left hand side, okay, O2, yeah, so 2 on the left hand side, and we have 2 with the carbon here, carbon dioxide here, and we put a big 2 in front of the H2O. So now we have 2 on the H2O as well. So we have 4 oxygens altogether on the right hand side. Okay. Put 4 in front of the oxygen, put 2 in front of the O2. Excellent, good. Right, because if we put a 4 in front of the O2, how many oxygens do we now have? Because it's 4 times by 2, isn't it? 8, yeah. So that now isn't balanced, is it? No, because we only have 4 on the right hand side. Now we have 8 on the other side. So what we can do is actually put a 2 in front of the oxygen. And now we will have 4 oxygens on the carbon dioxide on the left hand side, and 4 oxygens on the 4 oxygens on the 4 hydrogens on the left hand side, and 1 carbon on the left hand side, and the same goes for the other one as well. So if we try and write this out neater, just gonna rub this out so it's neater. This trying to balance a complete combustion equation is something that they will ask about a lot in the exams. So which is why I wanted you guys to figure it out without me putting up the answer, because then you're more likely to remember it. So does everybody understand how we balanced that word equation? Yes, good. So this is what we will get, which is what we got as well. So we put okay, so we have put 2 on the O2, meaning we have 4 oxygen, and we have put 2 in front of the H2O, meaning we have 4 hydrogen and 4 oxygen, and Yes, and carbon is 1. Carbon is 1 here as well. Okay, excellent. Right, next. So that's complete combustion. So remember, in complete combustion, you have enough oxygen, you have loads amounts of oxygen, and you can react fully with the fuel to break everything down, okay? So methane, oxygen, carbon dioxide, water, okay? And when this happens, you are making carbon dioxide and water, okay? Next question then. No, sorry, next. So what is incomplete combustion then? Does anyone have any idea about, because we already talked about what complete combustion is, so does anyone have any ideas what incomplete combustion is? Any ideas? Okay, so burning without oxygen, that's close, and there isn't enough oxygen. Excellent, good, yeah. So, sorry. Okay, so in complete combustion, you won't have enough oxygen. So there won't be enough oxygen so that the fuel won't react fully. And instead of forming carbon dioxide, so remember you get carbon dioxide when you react with, when you have complete combustion, you have loads amounts of oxygen, you will actually get something called carbon monoxide. And does anyone know the formula for carbon monoxide? It's a kind of a difficult one. So if you get it, I'll be very impressed. CO, excellent. Yeah, good. Yeah, so in carbon monoxide, you have CO. So carbon dioxide, as we said, CO2. Carbon monoxide is CO. Okay. Right. So we can, let me try and write out the word equation, and then we can try and figure out the chemical equation, which is harder to figure out. I'm not going to lie to you. So methane plus oxygen, but oxygen, remember, we don't have plentiful. So try and keep that in mind when you're trying to work out the chemical equation. And you have carbon monoxide plus water. Okay, so we're going to try and write this in a chemical equation, okay, with the chemical formulas. So anybody has any idea, then we'll try and balance it after that. So anybody has any idea how we would write this as a chemical formula with the letters? What do we think? Any ideas? How would we, what's the chemical formula for, what's the chemical formula for methane? We just mentioned this in the last bit. Chemical formula C4, close. CH4, excellent, good, yeah. So chemical formula for methane is CH4, okay? And so we've got the CH4. We've said that there isn't enough oxygen. So we won't actually put O2 instead because there isn't enough oxygen. We put O. Okay, so what's the rest of it then? CO, excellent, good. Sorry, we put, okay, sorry, O2, we have O2, CO, and then H2O. Good. And is this balanced? Is this balanced? What are we thinking? Does this look balanced to you guys? Okay, so let's try and work that out then. Is it balanced? So we will do the left-hand side, we'll do the right-hand side, okay? So we have 1 carbon, 4 hydrogen atoms, 2 oxygen atoms, because remember O2, okay? And then on this side, we have 1 carbon, 0, 1 oxygen, yeah, 1 carbon, 2 oxygen, and 2 hydrogens. This one's kind of harder to balance. So it's not balanced, is it? Because which one isn't balanced? The hydrogen isn't balanced, is it? So how can we try and balance this then? Any ideas on how we can try and balance this? What would your first step be? Okay, so right, so someone's saying add 2 in front of the H2O. Okay, so now we have so you times that by 2, you have 4 times that by 2, so now you have 4 hydrogens, and you have 2 times by 2, so 2 plus 1 there is 3. So now you have 3 oxygens. So how can we try and balance the oxygen on this side? This is a trickier one because we have 3 here and we only have 2 here. If we add 2 in front of the oxygen here, now we will have 4. So that's still not balanced, is it? But good try, that is good try. Then add 2. Okay, so the way that you would try and do this is because you want to get 3. So that's like an odd number. So if you see something like that, your first guess should be then I can have 1.5 or half of something, okay? So 1.5 times by 2, you get 3, okay? So it will be 1.5 or 1.5, 2. So you get 3 oxygens on this side, 4 hydrogens on this side, 1 carbon here, 3 on this side, and 4 hydrogens on this side. Does that make sense? Shall I try and write this out neater? Yeah? Any questions on getting 1.5? Okay, so I write this out neater. Yeah, so when you're trying to balance like 3 or 5, this one's kind of harder to balance. So the most likely you'll get in the exam is the complete combustion one. But this is just a good one to know as well. Okay, so the end product will be CH4 methane plus 1.5 or 1.5 of O2 atoms, forming CO plus 2 H2O. Yeah, so you can see that clearly isn't enough oxygen. Therefore, that's why it's forming carbon monoxide. And does anyone know anything about carbon monoxide in particular? Has anyone heard of carbon monoxide? Do we know anything about carbon monoxide? It's toxic. Excellent. Yeah, good. So carbon monoxide is really toxic and it's a poisonous gas. So in our houses, what we'll have is carbon monoxide detectors. And you might have heard in the news that people dying of carbon monoxide poisoning. And so you will have carbon monoxide detectors in your houses to try and see if there are any carbon monoxide, because it's that poisonous. And if there is, you'll be alarmed, and you can try and fix that, because if you breathe in too much carbon monoxide, it's poisonous and it can actually lead to death. So few people, you might hear in the news where people have actually died of carbon monoxide poisoning. So really, we really don't want to have incomplete combustion. We want to have complete combustion where you have enough oxygen and you're forming carbon dioxide and water. Okay, so does that make sense for everyone? Yeah, okay. So how can we really, so methane, oxygen, carbon monoxide, and water. Okay, there we go. So how can we really measure all of this? Measure like heat, basically heat energy, or change in energy. So energy can be released either in a chemical reaction as light, sound, or electrical energy. However, the way we will often measure it, or often it will be released as heat energy. So to try and see how much energy is being transferred, you can measure heat transfers, or the change in heat energy, basically. And that is by using something called calorimetry. It's a bit difficult to pronounce that word for me. So calorimetry is how you try and measure heat change. And has anybody done this sort of experiment at school? So you might have done it at school. Yeah, okay, so what will happen is that you will have a beaker. Okay, so you have a beaker. So this is a beaker, and you will have water. Okay, you have beaker, that will be water. And in here, you'll have a spirit burner. And in this, there will be a fuel. There will be different types of fuels, and you can try and see which one gives out the bigger energy change. So you'll heat this up, you'll heat up this water, but what you have to do at the beginning, because you're trying to measure the heat change, aren't you? So you're trying to measure the heat change. So what you'll do, you'll measure the temperature at the beginning before you put the fuel, before you put that under the spirit burner. And you will then heat this up using this fuel and the spirit burner. And then you will measure what the temperatures are again. So you'll measure the temperature at the beginning of the experiment, and you'll then measure the temperature at the end of the experiment, and then you'll calculate the temperature change. And then there's a few more calculations in it. And when you do that calculation and put in the temperature change, you can see the amount of energy that is being transferred. And we have measured that by using heat energy, by measuring the heat energy transferred, okay? So this is an experiment that you probably will do in science later if you haven't already done it. I don't know if anyone's done it has anyone done this already in science? If not, but this is an experiment that you will do in science later. And you can try and you can measure different types of fuels with this. So for example, if you used, oops, there's something in the chat. Not yet, no, okay, but you will do. So say if you're using one fuel, for example, it's methane, and you want to try and use an ethane, for example, you can see which one is kind of a better fuel, which one gives a better heat transfer by seeing the temperature change difference. So for example, if you use methane, and at the beginning, your temperature was at, the temperature was at 37 degrees. And it went up to, once you heated it for a while, it went up to, let's say 90, it was nearly boiling, so it was at 92 degrees. Whereas when you used ethane as a fuel, your starting temperature again was at 37 degrees. And the temperature went up to, and it was full on boiling, so that was 100 degrees. Which one will be the better fuel? Because which one is providing more heat transfer? What do we think? Ethane, excellent. Why is it ethane? Because there is a bigger energy difference, bigger temperature difference here, isn't it? So it's heating up the water way more than methane is. So ethane will be a better fuel. So there will be a couple of things that you'll need to keep constant in this experiment. What do you think those things might be? Any ideas on what you might need to keep in this experiment the same so that it is, so it will be ethane that's the better fuel because you're getting a bigger temperature difference in ethane because your starting temperature for the water was 37 degrees. And when you heated it, it went up to 100, whereas methane, the temperature only went up to 92 degrees. Okay, so the better fuel will be ethane. Right. And yeah, so there'll be a few things that you'll need to keep the same in this experiment to try and make sure that it's fair. What do you think those few things might be? Any ideas on what those few things might be? To make sure we always want experiments to be fair. We want to do fair testing in experiments. Any ideas what things you could keep the same in this experiment to make sure that it's fair? So you do it, your friend do it. What do we need to make sure that you keep an eye on? Any ideas? Okay, excellent, good. So one of them is the, could be the same amount of water, yeah? There is something to do with the water, more than the same amount of water. What else could we keep with the water? So for example, say if my starting temperature for the water was 38 degrees, this was still 37 degrees. This isn't a fair testing, is it? And say if ethane only went up to 92 and methane also went up to 92, we have to say that we can keep the starting temperature of both of the, in both experiments the same. We might want to keep the same amount of water. Okay. Same amount of water, starting temperatures to be the same. Instead of amount of water, what's a better word to use for than amount? A bit more specific. Volume, excellent, good, yeah. So we want to keep the volume of the water the same. We want to keep the starting temperature of the water the same. There's one more thing that we can try and do. So for example, if your friend was doing this experiment and they had the spirit burner really close up to the beaker, and for you were trying to keep it a bit away because it's really hot, is this experiment fair? Are we keeping this experiment fair? Would you and your friend be measuring the same thing if you had yours way further away, the spirit burner further away, and your friend was close up? No, it won't be fair, will it? Because why would that be? No, because yeah, exactly. So if the spirit burner is closer up to the beaker, then of course the beaker is gonna get way hotter because it's closer to it, isn't it? Whereas you're holding it further away, then it's not gonna get the same amount of heat. So what you need to make sure, one of the key things that you need to make sure with this experiment to ensure that it's fair, and that both of you are testing the same thing, is making sure the distance between the fuel or the spirit burner is the same for both. So distance from the spirit burner to the beaker is the same for both of you. So for example, if one of you is keeping it away at 10 centimeters away from the beaker, and one of you is also keeping it away 10 centimeters of the beaker, then we know it's fair because you're keeping it the same distance away from the beaker. Okay? However, this doesn't necessarily mean that all of that heat is going to the beaker. Okay? So what can we try and do to make sure that all of the heat is going to the beaker? beaker. So we kept it at the same distance, but then again, that doesn't necessarily mean all the heat is going to the beaker. So what can we make sure that heat is basically not lost? Any ideas? How can we make sure the heat doesn't escape? Okay, so one way we can make sure the heat doesn't escape is by adding a lid. Okay, so we can add a lid to this beaker so that heat is basically trapped in. You can add insulating layers, so you can maybe wrap it in a tin foil or something like that to try and keep the heat in. But you just need to make sure if you're doing it, so is your friend doing it. So you can't keep the lid on and then your friend doesn't keep the lid. You keep the lid on and your friend doesn't keep the lid on, then it won't be a fair experiment. Whatever measures you're taking to make sure the heat is trapped inside, both of you will have to do it. Okay, so that's calorimetry and something and a way you can measure energy transfer. So remember we looked at those energy enthalpy diagrams with the endothermic and exothermic reactions. One of the practical ways you can actually measure this is by doing something like this. Okay, does that make sense for everyone? That is combustion. Okay, next we're going to look at thermal decomposition. So thermal decomposition is when we use heat to break something down. So combustion, remember, was burning it with oxygen. Thermal decomposition, so if you break the word down, is thermal, meaning heat, and decomposition just means breaking down. So breaking down using heat. And whereas combustion was an exothermic reaction, because you're making bonds and you're releasing heat, now breaking down something with heat, you're taking that heat in. Therefore, it is an endothermic reaction. Okay, so an example of this can be metal carbonates. So copper carbonate, sorry, not copper, yes, copper carbonate, breaking it down to give metal oxide and oxygen. So these reactions are very, they can be endothermic and they will take heat in. Okay, so this equation, is this balanced? Yes, it is balanced, yeah. So that was kind of a question, it is balanced. How can we tell if it's balanced? Because we just do left-hand side, we do our right-hand side, you can see there's one, 3 oxygens, 3 oxygens. Yeah, so there's 1 carbon, 1 copper, and 3 oxygens. Okay, so this is an example of thermal decomposition, which is just when you use heat to break down substances. Okay, so let's go on to doing some practice questions then. So the diagram below shows a candle burning in air under a bell jar. So when candle burns, there is a reaction. So to give the chemical formula of the products of this reaction. So we have to be very careful here because we want to give the chemical formula. We don't want it to write it down in words. We want the chemical formula for this, okay? So what is actually happening here then? You're burning the candle. So what will be the products that come out of this reaction? Any ideas? What are we thinking? So I'll give you guys a clue. This is an example of combustion. What would be the products of that combustion then? Because you're burning it with heat, you're burning it with oxygen. Excellent, carbon dioxide. But I want you guys to be careful because I don't want the word, I want the chemical formula. So what's the chemical formula then? CO2, excellent, good. So one of the products will be CO2. Good. What about the next one? What was the other product you get? when you have combustion, which is what's happening here, by the way. H2O, excellent, good. Water, yeah, you have CO2 and H2O. Excellent, you guys are really getting this. Right, next question. Yeah, so because they've said chemical formula, which is why it's really important that you read the questions properly, because carbon dioxide in theory is right, because you do get in complete combustion, you get, so we said methane plus O2, so oxygen, it gives you carbon dioxide and water. But because they've said chemical formula, you need to be careful and actually give CO2, H2O. Right, next question then. So as the candle burns, some of the candle wax is used up. Give 2 other observations which would show that chemical reaction is taking place. Okay, what are those observations? Let's see. Okay. Okay, so somebody said heat. Can we explore that a little bit? Can we explain that a little bit? What do we mean by heat? Okay, so are you trying to say that there'll be an actual fire? So there'll be heat and fire coming out of the, yeah, okay, so you can see the smoke, excellent, good. You'll be able to see the heat and you can feel the heat and you'll see the fire. Any suggestions? How do we know that the candle wax is being used up and the chemical reaction is actually taking place? So you guys have said you'll be able to see the smoke, you can see the smoke, you'll see the fire, or you see the flame, you'll see the flame. The steam, yes. So what's happening in the steam then? What is the steam? Maybe be a bit more specific. So yeah, it's water, isn't it? So it's H2O and it's the condensation. Yeah, so condensation, you'll be able to see that on the covering of it. So the bell jar itself. Inside of the bell jar, yeah. Any other suggestions? So you'll be able to, the smell, yeah, you might be able to smell it, okay. There'll be soot as well, yeah. So when you're burning something, you guys, do you know the black thing that kind of comes up? So you might be able to see that as well. So that's kind of the black thing. So that's the last thing I would say. The main things you would want to try and see is that condensation is really one to talk about, that you'll be able to see this steam and that there'll be water, basically water droplets in the inside of the bell jar. You'll be able to see the smoke, you'll be able to see the flame as well, the actual flame showing that the candle is being used up. Okay, so these are just suggestions and most of them we have got. Okay. Okay, right, next question. Okay, so figure 2 shows the reaction profile of an exothermic reaction, which does the energy value of 1,370 kilojoules represent. So that's the arrow here. Which one is that showing? What do we think? What is that arrow showing? Excellent, yeah, so this is showing activation energy. Yeah, so the right answer here is activation energy, because remember, if we go back to the enthalpy diagrams, from where the reactants are to the top of the kind of curve, so top of the curve here, this is the activation energy. That's what it's representing, because that's the amount of energy the particles need to collide with I remember activation energy is the amount of energy the particles needs, the amount of energy the particles needs to collide with to make sure that there is a successful collision. Okay, so it is activation energy. So it would be a good idea to kind of memorize the different parts of the enthalpy diagram, because you will get quite a few questions on it. So yeah, activation energy. Right. I believe this is our last question. Okay. So when magnesium burns, it transfers something and something energy to the surroundings. We say that it is a something reaction. So what do we think the answers are for this one? So you can pick the options at the top of the question. So what do you think? And when magnesium burns, it transfers something and something. What is it transferring? What kind of, yeah, so it's transferring heat. I don't know if you guys have done this experiment. You hold a magnesium strip to a Bunsen burner, it kind of lights up. It's kind of pretty. So heat, what else is it transferring? Kinetic energy, maybe. So it lights up, so it's lighting up. So it's transferring light energy to the surroundings. And what kind of reaction is it? So kinetic energy, just to clear up, is movement, okay? So we say that particles have kinetic energy because remember, particles are moving around. But in this case, it's transferring heat and light. And what kind of reaction is it? So I'll give you guys a clue. It's between endo and exo. What do we think? Exothermic, excellent, yeah, good. So it's a type of exothermic reaction. Yeah, excellent. So that'll be the end of our question. So we're coming to the end now, and I'm going to ask you guys the same question again that I asked at the beginning, which is how much do you guys feel like now you know about this topic? How confident do you guys feel? So I'm going to relaunch the poll. How are you guys feeling about this topic now? Yeah, so most of you saying that you know most of the topic, which is really, really good. One of you said that you feel like you know all of it, which is excellent. And yeah, so that's really good to see. Hopefully you guys have found that useful. And I just want to say in the chat, we put the feedback form. So if you guys could fill that in, that'd be really great. So that we can see what the feedback is and tailor the lessons to your liking, so you guys can get the most benefit. So just make sure you fill that in at the end once you're done. And is there any questions or anything that you want to kind of quickly go over? Maybe anything? No questions. Okay, so we're just going to quickly look at the clinical skills corner. And what I want to talk about, like I mentioned at the beginning, is actually the treatment for burns, because we talked a lot about combustion, thermal decomposition, and using the Bunsen burner and stuff like that today. So what is the treatment for burns? Does anyone actually know? What if you were making a cup of tea, or or even in your science labs, you were using the Bunsen burner and accidentally caught your hand. what was the first thing that you should try and do? Yes, so you should put it under cold water. So you need to make sure that it's not um, really, yeah, so you should make sure that it's really, it's cold and it's kind of, it's not freezing cold, like ice cold water, but that it's relatively cold. But before you do that, you just want to make sure that you remove any sort of jewelry or anything like that. And but you have to be careful, because if anything's kind of stuck to the burn, if you've had quite a bad burn and it's quite anything, any jewelry stuck to the burn, you don't want to remove that, because obviously in essence you could try and maybe hurt yourself even more, maybe tug at the skin or something like that. So you want to remove the jewelry if there's not anything on it, if it's not kind of next to the, right on top of the burn. Then you want to run it under cold water, preferably for 10 minutes. And if it's still kind of red, you want to run it under for longer. Yeah, you could put Vaseline on it, maybe put maybe a special plaster. Yeah, all of those things. There's different levels of burns. There's a 1st degree burn, 2nd degree burn, 3rd degree burn, and it also just depends on what layer of the skin has been damaged. So you have different layers of the skin, like your dermis, your epidermis. So if those layers have been damaged, obviously you need more care and you do need to go to the hospital. But if it's just kind of a 1st degree burn, you can just run it under cold water. Obviously, if that's happened at school, tell your, I'm guessing if it's in the science lesson, tell your science teacher, whoever it is, run it under cold water. If it really hurts, pain relief and things like that. But the best way is prevention is better than anything. So just be super careful when you're using things like that at home or at school as well, so you don't hurt yourself. So yeah, that's the end of our session today. Hopefully you guys have found it useful and learned something from it. Any questions, put it in the chat. If not, I will see you guys later. And remember, you also get the link for the recording. So if there's anything that you guys want to go over, just review the recording as well. Okay? Thank you so much, everyone. Thank you.